So ADCs, or analog to digital converters, are used to convert an analog voltage present on a pin into a digital value. So this is very useful, as many sensors that we use output an analog voltage. So lots of sensors are not compatible with GPIO pins, for example. With a GPIO input pin, they can either read 3.3 volts or 0 volts, nothing else. But with a A to D, we can put in any voltage within a particular range. So we've seen examples of how we use these before. So we get the red line here representing our analog signal changing over time, and then we sample this signal at discrete points in time, and then for each kind of each value we give it, each level is represented by a binary value. And so by reading those values at these discrete time points, you can build up kind of digital version of that signal, for example, which will then transmit. So this waveform comes into our A to D, which then will create this kind of digital representation of that signal. We can then send it over a radio link or optical fiber or whatever, and then using a DAC on the other side, we'll be able to recreate that signal on the output. So this is where we use DACs, but also just for sensors, you might get a temperature sensor where the output voltage is proportional to the temperature, and so on. So when we want to connect that to a microcontroller, we need to use an A to D or ADC. So on this LPC176J, again we've got the core, different memories. Then we've got this A to D peripheral. So this is an input represented by these this arrow here. What's connected up through this bus system up to the core. So then in our software we're able to access essentially the voltage what's on this pin. So looking at the pin mapping for the embed, you can see this is represented by this orange box here. It's analog in. So there's 6 analog pins on here that we can use. So that peripheral, it's connected up to 6 of these pins, and the peripheral lives in this APB0 peripheral. So this is where all those registers live in memory. So the actual microcontroller itself has actually got an 8-channel ADC, but only 6 of those 8 channels are connected to these external pins we can use. So on the microcontroller, there's actually 8 pins, but only 6 of them are connected to kind of the embed pins, and that's pin 15 to pin 20. So you need to make sure that you only use those pins when using the ADC. So it's actually a 12-bit ADC, meaning that the voltage is converted into a binary value based in this 12-bit range, so from 12 zeros up to 12 ones. So in decimal that goes from 0 to 4095. So depending on the voltage, it's going to give us a decimal value in the range 0 to 4095. So the actual analog voltage on the pin is referenced to 3.3 volts. So this that basically means this 4095 is 3.3 volts, and 0 corresponds to 0 volts. So obviously if you went the value directly in the middle there, whether it's going to be 2000, what's that, 47 or something like that, that would correspond to 3.3 over 2. So it's just like a linear scale between 0 and 3 volts, 3.3 volts, mapped to 0 to 4095. So it means the resolution of the voltage we can read in is 0.8 millivolts. So we've got our maximum range 3.3 volts divided by these 4096 steps. So we go back and look at this picture here. So these would actually be 12-bit values. So this corresponds to 3.3 volts. that this top line would be 40, what was it, 95, I can't remember. And the bottom would be 0, what corresponds to 0 volts, and then the gap between each one of these would be 0.8 millivolts. So the ADC is implemented using a successive approximation approach. So this basically means the ADC, it compares the input voltage to a voltage that's generated internally via a digital to analog converter. So inside the ADC, there's also a DAC. So each bit of the DAC has got an equivalent voltage weighting. So you can see here, bit 11 essentially corresponds to 1.65 volts, so that's half. So we say V is equal to 3.3 volts. That's basically V over 2, V over 4, V over 8, and so on. And we can see we get down to our resolution, so that's the smallest resolution we can get. So basically it reads the most significant bit is tested first. So the internal DAC outputs 1.65 volts, and that's fed into a comparator along with the analog voltage on the pin. And then the comparator checks which is the largest. So if the input voltage on the ADC pin is larger than 1.65 volts, then bit 11 is set to be a 1, otherwise it's set to be a 0. Then we would test bit 10, so whatever that value was, so 0.25, we check is the is the input voltage greater than this or less than this, and depending on the answer, it would then use it to set bit 10 to be a 1 or a 0. Then we'll do bit 9. So when you start reading in the values, it would start from here. It'll say greater than this, less than, greater, and as it goes through at each step, you end up then with the digital value that corresponds to that voltage. So because it actually takes time to do this conversion, so for each bit we've got to put the value into the comparator, output the value from the DAC and so on and compare it. It actually takes a finite amount of time, so that means the conversion rate is limited to 200 kilohertz. So it's not a particularly slow process, but this has limits to the kind of frequency signals that you can read into the A to D. Because from Nyquist's theorem, the sampling. This is a max. This is a maximum conversion rate. So this will limit the kind of. If you wanted to put a sine wave into the A to D, maximum would have to be 100 kilohertz.